Welcome to TalkTensors. Today we're doing a deep dive into some really interesting machine learning research.
That's right. We're looking at how AI agents learn, specifically how they can get better at generalizing what they know.
Exactly. It's a big challenge, right? Getting AI to work well, not just on the task it trained on, but on new, complex stuff too.
And this paper we're discussing, it tackles that head on. It's called A Representational Framework for Learning and Encoding Structurally Enriched Trajectories in Complex Agent Environments. Bit of a mouthful.
Yeah, definitely.
Yeah.
But the core idea is powerful. It's about giving AI a richer way to understand its experiences.
Right, because many current AI agents, well, they learn representations that are maybe too simple. They lack a certain structural depth.
Which means they struggle when things change. They're not truly adapting.
Precisely. You see these amazing results in games or specific robotic tasks, but change the setup slightly.
And it falls apart. Needs to relearn everything.
This paper argues that the problem lies in the representation, how the AI internally models the world and its actions.
So the solution they propose involves these things called structurally enriched trajectories, or sets.
Yeah, and an architecture to learn and use them, called SETL. Structurally enriched trajectory learning and encoding.
Okay, so before we get into the nitty-gritty of sets and SETL, maybe let's step back. What's the context here? How did we get to this point in representation learning?
Sure. Well, the whole field of state representation learning has come a long way. Early on, it was often about, hand engineering features.
Humans deciding what was important for the AI to pay attention to.
Exactly. Then came deep learning, and that changed things quite a bit. Neural networks started learning these features automatically from raw data.
Like CNNs for images, RNNs for sequences, that sort of thing.
Yeah.
Big breakthroughs.
Definitely. But even with those powerful tools, the learned representations often missed the relationships between things in the environment. It was more pattern recognition than, say, structural understanding.
Which is where ideas from cognitive science started to seep in more, right? The idea that humans use hierarchical knowledge structures.
And that led to increased interest in structured representations in AI. Things like graph neural networks became really important.
Because graphs are all about representing relationships, nodes, edges. It's a natural fit for modeling interacting components.
Precisely. And this paper really builds on that. It acknowledges earlier approaches like hierarchical RL, goal-conditioned RL.
Disentanglement techniques. People were trying to add structure.
Right. Breaking tasks down, focusing on goals, separating factors. But the authors here felt something was still missing.
What was that?
A way to represent the entire trajectory, the sequence of interactions in a structured way that captures not just what happened, but the underlying causal links and future possibilities, what they call affordances.
Affordances.
Yeah.
Like what actions are possible given the current state and objects?
Kind of. It's about the potential interactions and their likely effects based on the agent's abilities and the environment's properties. Understanding that helps predict how actions will influence the trajectory.
So classical RL often just had these flat sequences, right? State, action, next state, reward.
Pretty much. The Markov assumption, basically. What matters is the current state. But for complex long-term tasks, maybe that's not enough. You need to track sequences and dependencies over longer timescales.
And things like the options framework tried to add hierarchy, but maybe didn't go far enough in structuring the trajectory itself.
That seems to be the argument. They needed more detail, more explicit structure about objects, interactions, and these affordances to really enable generalization.
Okay, so that sets the stage for sets and SETL. Let's get into it. What exactly is a structurally enriched trajectory?
So think of a standard trajectory states actions. A SIT goes beyond that. It incorporates objects within the states, the specific interactions happening, and these learned affordances.
So it's not just what happened, but how the different elements contributed.
Exactly. It's a richer, more detailed story of the episode. And SETL is the system designed to learn these sets and encode them.
How does it do that? The paper mentions hierarchical subgraphs.
Yeah. SETL represents each set as a hierarchical graph. Think levels of abstraction.
Okay.
At the lowest level, you have objects and interactions. Maybe the agent pushing a ball. SETL learns representations for the ball object and the pushing interaction.
Makes sense.
Then, at a mid-level, states are represented as graphs of these interacting objects. And affordances act like links between these state graphs, capturing the transition dynamics, how one state likely leads to another based on interactions.
And the top level.
That's the overall set representation, the whole trajectory structured hierarchically.
And what's this about a hierarchical memory structure?
Right, so SETL doesn't just look at one set in isolation. abstraction. It stores multiple sets in a larger structure, like a big heterogeneous graph.
Heterogeneous meaning different types of nodes and edges. Objects, interactions, affordances, states.
Precisely. And crucially, components can be shared across different sets. If the agent interacts with the same ball object in 10 different episodes...
So that ball node is shared in the memory.
Exactly. This allows the system to build up knowledge about that object across different contexts and tasks. It's key for transfer learning.
That's pretty clever. It's building a more connected general understanding.
That's the goal, moving beyond isolated episodes to find common patterns and structures.
So they needed an environment to test this, right? You mentioned create.
Yeah, the create environment. It's designed for this kind of thing, multiple tools, objects you can manipulate, different goals. It forces the agent to generalize actions.
Okay, so how does Settle actually build these graphs in practice?
Well, in their experiments, they first let an RL agent explore the create environment randomly, just generating lots of trajectories.
Gathering data.
Right. Pushing balls, interacting with things. Each episode is then labeled success or failure based on whether it reached the goal.
And then Settle constructs a set graph for each episode.
It identifies objects. They used a pre-trained model called SAM for that in the experiments.
Segment anything model.
Yeah. Then it learns representations for the interactions between the agent and these objects. They used a specific technique, a conv-LSTM encoder with triplet loss.
Triplet loss. That's about making similar things close and different things far apart in the representation space, right?
Exactly. They wanted to make sure, for example, that interactions with bouncy objects clustered together separate from interactions with fixed objects.
Okay, so objects identified, interactions learned, then the mid-level.
States become these graphs of interacting objects, and affordances link these states, capturing the transition dynamics like we talked about. These affordances aren't just immediate effects, they try to encode longer-term consequences too.
Improving reasoning about what happens next.
Hopefully. And then the full set graph is built for the episode and stored in that hierarchical memory. For practical reasons, they then learn a compact latent representation like an embedding for each set.
Right, you need something computationally manageable for downstream tasks. How is that embedding learned?
They use a graph encoder. Specifically, they adapted an existing approach called heterogeneous co-contrastive learning, or HECO.
Okay, HECO, but adapted how?
HECO was originally designed more for static graphs, like social networks. Settle adapts it for these dynamic, episodic trajectory graphs. It treats each set graph as a subgraph within the larger memory, with the set node itself being central.
And they use triplet loss again here.
Yes, triplet loss on the set embeddings themselves, to cluster trajectories with similar outcomes or dynamics together.
But they also mention a hybrid loss.
Right. They combine the set triplet loss with a cross-view contrastive loss drawing from the HECO approach. The idea is to make sure the embedding is consistent even when you look at the set graph from different perspectives.
Give perspectives, like where?
They define two main views.
Yeah.
A network schema view based on the different types of nodes and edges, and a metapath view.
Metapaths, what are those?
They're sequences of node types connected by edge types, like set node, state node, object node, interaction node, affordance node. These paths capture specific kinds of semantic relationships within the graph.
I see. So the hybrid loss encourages consistency between the overall structure view and these specific semantic pathway views.
Exactly. It helps ensure the learned embedding captures both the local structure and the higher level relational information robustly. They use specific metapaths focused on capturing causal chains and state transitions.
Okay, that's quite a sophisticated encoding process. So how did they evaluate if it actually worked?
Their experiments focus mainly on analyzing the quality of the learned set embeddings. Could the embeddings distinguish successful from unsuccessful trajectories? Could they group similar tasks together?
What did they find?
First, they looked at the margin parameter in the triplet loss. They found that in the create environment, which is relatively simple, larger margins seem to work better.
Suggesting a need for clearer separation between the embeddings of different outcomes.
Possibly, yeah. They also visualized the embeddings using PCA and k-means clustering. The visualization showed that Settle could indeed separate successful and failed attempts within the same task. It also seemed to capture task-level similarities, grouping different tasks that shared similar underlying dynamics.
That sounds promising. What about the comparison between the simple triplet loss and the hybrid loss?
The hybrid loss appeared to give better separation between different tasks, especially those with shared structures. It also tended to pull the positive and negative outcomes within the same task a bit closer together.
Closer. Why is that good?
Because the cross-view contrastive part of the hybrid loss forces the model to find representations consistent across different structural views. This likely helps it better encode the shared dynamics of the task itself, regardless of the specific outcome.
Okay, that makes sense. Did they compare settle to other state-of-the-art methods?
They argue that direct comparisons with encoders like the original Hucko or another one called GTC are difficult because those were designed for static node-centric graphs, whereas settle deals with dynamic, episodic, trajectory-centric graphs. It's a different problem setting.
Fair enough. Did they do any ablation studies?
Yes, crucial part. They systematically messed with the settle architecture to see what broke.
Like what?
They tried randomly removing a chunk of the states within a trajectory. Performance dropped. They tried shuffling the order of states, breaking the sequence.
Performance dropped again.
Significantly. Showed the importance of encoding that sequential, cumulative information. They also tried flattening the representation, getting rid of the hierarchical graph structure.
And that hurt performance too.
Big time. Which really underscores the value of that explicit relational structure they built in.
So the experiment seemed to back up the design choices. The hierarchy, the sequence, the structured representation, they all seem important.
That's what the results suggest. It's evidence that this way of representing trajectories helps capture meaningful, transferable information about tasks.
So, wrapping up the paper's findings, what are the main takeaways and implications?
Well, the big takeaway is that sets and settle offer a novel framework for representation learning in RL. It moves beyond just compressing states or using flat trajectories.
It's about explicitly modeling the hierarchical structure of tasks and interactions.
Right, using heterogeneous graphs, the hierarchical memory, encoding entire trajectories. It allows the system to build a task-focused latent space.
Which should, in theory, lead to better generalization across tasks.
That's a key implication. By capturing these multi-level relationships and recognizing shared components like objects or interactions across different experiences, the agent can hopefully transfer knowledge much more effectively.
It feels a bit more like how humans learn, maybe, identifying meaningful chunks or substructures and recombining them.
Exactly. The paper draws that parallel. Many AI models struggle with that kind of compositional flexibility. Settle's graph-based approach offers one way to achieve it.
And it connects to lifelong learning, too.
Definitely. The hierarchical memory structure could help agents continually learn, adapt to new tasks, and potentially mitigate catastrophic forgetting where learning a new task makes the AI forget old ones.
By retaining and reusing those shared lower-level components.
Precisely. It's about building a cumulative knowledge base that connects abstract concepts with concrete execution details.
So it's contributing to this bigger picture of structured intelligence in AI.
I think so. Linking low-level perception and action with higher-level reasoning and planning, of course, they acknowledge limitations.
Like scalability, these graphs could get huge in complex environments.
Yeah, computational complexity is definitely a challenge, they mention, and efficiency in very high-dimensional state spaces. Future work needs to tackle those issues and also look more directly at how these representations impact actual policy optimization and planning.
Makes sense. It's a foundational representational framework, but integrating it fully into decision-making pipelines is the next step.
Right. Okay, so that brings us to our novel notions segment. Where could this research lead next?
All right, let's brainstorm some ideas. What's first?
Okay, so settle currently assumes a fixed set of known objects and interactions, right? Defined in its initial ontology.
Yeah, they mentioned using SAM to identify objects, implying some pre-existing categories.
So, idea one, dynamic ontology enrichment. What if the agent encounters something completely new, an object it's never seen, a new way things can interact?
How would it cope? The current system might just fail to represent it properly.
Exactly. So the idea is to combine settle with techniques from, say, continual learning or meta-learning. Maybe the agent could learn to detect anomalies, sensory patterns that just don't fit its current world model.
And when it detects an anomaly,
it triggers a process to expand its ontology. It dynamically adds a new object or interaction type to its repertoire.
Could the settle hierarchy help with that?
I think so. A new object node could be added at the bottom level. Then, through interaction, the agent could learn its affordances, how it affects state transitions, maybe even relate it to existing similar concepts using transfer learning.
That sounds super useful for robots in unstructured environments like search and rescue. They constantly encounter novel things.
Absolutely. And maybe the agent even gets better at learning new concepts over time, a kind of meta-learning about ontology expansion.
Okay, cool idea. What's number 2?
How about counterfactual set generation for improved planning?
Counterfactuals, like what-if scenarios.
Exactly. Right now, settle represents what did happen. But what if the agent could generate representations of what could have happened if it acted differently?
Why would that be useful?
Deeper understanding. It could learn why certain approaches failed, or how a successful trajectory might have unfolded differently. It relates to causal reasoning.
So you'd integrate generative modeling, train a model to generate alternative sets.
Yeah, conditioned on an initial state and maybe a hypothetical action or outcome. And the beauty is, because set sets are structured graphs.
The generated counterfactuals would also be structured graphs, not just pixel predictions or state sequences.
Right. You'd be generating structured what-if scenarios representing hypothetical objects, interactions, and affordances. More interpretable, potentially more accurate.
I could see that being useful for analyzing tricky situations like near misses and autonomous driving. Why did this almost happen? What small change would have led to disaster?
Precisely. Or even identifying critical decision points by comparing successful sets with generated unsuccessful counterfactuals. It could guide exploration.
That's a fascinating direction. Pushing beyond just representing experience to reasoning about possibilities.
Of course, both these ideas are speculative, building on the paper's foundation.
Naturally. But they show the potential that opens up when you start thinking about richer, structured representations.
Definitely. This work on sets and settle is, I think, a really valuable contribution. It pushes us towards AI that doesn't just learn patterns, but starts to understand the underlying structure of tasks and environments.
A step towards more adaptable general intelligence. We really do encourage you, the listener, to check out the original paper. The link's in the description.
Yeah, it's worth the read. And it leaves us with a thought. As we develop these more sophisticated ways for AI to represent knowledge, how fundamentally will that change their ability to learn, reason, and interact with our complex world?
Something to ponder.
Yeah.
Thanks for tuning in to TalkTensors.